welcome to this video. My name is Ochoke, software engineering student at Macquarie University. So today I'm going to be taking you through a project we are doing, me and my group members, as you can see on the screen. So I'm going to take you through. So I beg you stay so that you can understand, because it's a very interesting project, and yeah, it's worth giving it your time. So our project is called Graph-Based Reasoning Large Vision Models for Uganda Sign Language Translation in Infectious Disease Screening. Yeah, so you should stay around so that you can get to know more about the project. Yeah, so we need to first understand the background of how we got the idea of this project. We realized that over 500,000 deaf Ugandans, they always struggle when they go to the hospital. They struggle to like describing their symptoms so that they get desired treatment or immediate treatment. That's why we came up with this idea, and then so we needed to focus this project on those serious diseases, infectious diseases, so that to avoid pandemic and then those kind of things before it's too late. So our system translates Uganda Sign Language in real time, and then currently it still focuses on only 8 clinical slots. For example, fever, cough, duration, and then some others that you're going to see later on. So the main aim of this project is not to completely shut down the need of human translators in the clinical sectors. And the project is just there to reduce intake time so that deaf people they are saved immediately, so that before the condition escalates. Yeah. So we need to first look at related works that have been done close to our project. When you look at 2018, Bilokovic, they worked on graph attention, the one we are currently working on. You're going to see. And then looking at 2021, the vision transformers was worked on. And then 2018 also, GCN was worked on. And then 2020, post-based sign recognition was also worked on. And then the key gaps, if you look at this table, you will see that none of this talks about graph. There's no graph-based medical sign recognition. There's no Uganda Sign Language datasets or models built already, and there's no H deployment for clinical systems. They're not there. And then there's no red flag detection to show that this is a serious condition or it's not a serious condition, and stuff like that. And then if you look at the problem statement, you see that deaf patients, they cannot explain symptoms to doctors, and when you go to hospitals, you won't find human interpreters there 24/7. Most of them they work for a specific time and then they leave. And then most times they're always delayed triage, which leads to outbreaks, or in case of maybe like serious illnesses that need to be taken seriously. So if it's not taken seriously, once it's delayed to be worked on, let me give an example of Ebola. So if a deaf person has Ebola and then they're trying to explain but the doctor is not understanding, once it's delayed, it means many people will be affected because of computational problems, and there are no continuous sign recognition yet, and then sign up variation due to and poor video quality, and then extracting 8 clinical slots accurately. It's something we are looking forward to working upon it. And then I'm building a system which is the size is less than 400 MBs, and then the speed is less than 300 milliseconds on 100 tablets. And then looking at the research questions and objectives, we needed to find out if graph attention network can capture Uganda sign language signs robustly, and then how to fuse RGB plus pulse streams, and how to transfer from American Sign Language or Ghana Sign Language to Uganda Sign Language, and how to ensure clinical safety with red flags. And then the objectives is to design graph attention network for 468 landmarks, which implies 10 to 15% what error rate worked on, and then to build a multi-stream large vision model, which leads to 80 to 85 to 85 to 90% slot accuracy, and then to add FST constraints for valid medical logic and to deploy a system which is fast. The speed should be less than 300 milliseconds on 100 tablets. And then looking at research contributions, we have worked on graph resonant recognition, which is four layer with skeletal and plus semantic edges. This one improves is 20 to 30% better than CNNs, which are poor with lightings and maybe when some with sign variations and stuff like that. And then looking at the second contribution, FST constraints are being fixed to enforce medical question and answers accurately, and we are to produce a system which is the first Uganda Sign Language medical AI in East Africa. The size should be less than 200 MBs, and then the speed should be less than 300 milliseconds. And we should implement fast earth interoperability resources plus red flag detections, which improves earth screening by 95%. System architecture generally. So the patient loads the video, then MediaPipe holistic identifies the landmarks on the body, which is supposed to be 468 landmarks in total. But then when you remove the face, because we didn't consider the face, so it reduced to 75. So we'll be only considering the hands and then the body, with the exception of the face. So after that, the 75 nodes or the landmarks detected from the patient video goes through graph building to find some connection between the nodes and then the edges. Then graph attention model helps to map the nodes or the build nodes and edges together to clinical slots, and then afterwards they produce JSON file which helps in red flag detection to produce red flag detection alerts. So the first model we chose was pulse extraction. So this is its architecture. So with pulse extraction, the blaze pulse, it has the blaze pulse plus manohands and then flame face. So with the last two, you can see manohands focuses on the hands, and then flame face focuses on the face, and then blaze pulse on the body. Yeah, so it takes video input, the RGB video input, and then the output should be those landmarks detected on the body. And then we optimized our first model, the model 1, and with the symbols. The PT is the landmarks detected at a time, and then position plus visibility, as you can see, the XI, YI, and then ZI, because every single point marked on the body it's supposed to be having 30 numbers on them. That's the X-axis, Y-axis, and then Z-axis in 3D space. Yeah. So I stands for, it represents the landmarks detected on the body from 1 to 468. And then the mathematical output, we are supposed to get the 468 landmarks detected on the body, but then ours was downsampled to 75 nodes, which only focuses on the body and the hands only. And then the second model, graph attention network, this is its architecture. It loads the 75 nodes from the previous model, extracted from the previous model. After loading, it multiplies by RGB. So with RGB, and then it goes to the first layer. After the first layer, it gives the first layer gives it to 64 dimensions, so that the model can learn faster, and then the second one increases to 128, so that the model increases its possibility of learning from different angles and stuff. And then the third layer increases also the dimension, and then the last step is global pooling, where after learning it comes back to match everything together, so that it finds out the final conclusion from it all, and then it maps to one of those 8 clinical slots. Actually all of them, because they're supposed to be given percentages from each of them. Yeah, so it maps to so these are the formulas. As you can see, it starts with the input, the 75 nodes or the landmarks detected from the body and the hands, and then the graph attention or the GAT has 4 layers. The 4 layers, they run through it so that the model can learn. The 8 attention nets, it increases the possibility of the model learning faster and accurately. Because if the model is learning, let's say the node we are focusing on is the hen. So if the model is learning, trying to learn what the hen is doing, it can consider the hen direction, the speed, the position, and stuff like that. It is a lot of things to consider. The 8 attention, 8 different things at the same time. So after that, it merges all of them together, and then it gives the final one. So the mathematical steps, with the mathematical steps, the linear transformation that's where it gives it dimensions. If it's focusing on a hen, it gives it like 64 dimensions, so that the model can learn in different ways from the same point or from the same thing. And then the attention score, it calculates the attention of the neighbors at a given time. So if we are focusing on a hen, so it means when it's focusing on a hen, the neighbors will be the fingers and then the rest. So at a given time, when someone is trying to sign in front of the camera or stuff like that, so the attention score is to find which neighbor is more important at a given point. Yeah. And then finally the aggregation, it merges all of them together. And then output, the output, it maps to the clinical slots. And then the data set we used, we got some data set from Kaggle, and the data set has a total of 9,877 videos, which we analyzed 500 samples of those videos, and then the quality is excellent, and then it's 100% usable with no corrupted files. So, and inside the data set, they're in categories. 27. That's 27. 27 categories. One we were focusing most on was infectious disease and prevention, which has only 186 videos. And then other specialties like the dental, orthopedic, respiratory, nutrition, and so on. So in the videos, the duration distribution and the data quality assessment, we got 0 corrupted files, consistent resolution. It has all its videos has the resolution of 1920 by 180. Stable frames, they all have 30 frames per second, and no missing metadata, has metadata, and it was 100% suitable for training our model. So the visualization, as you can see on the screen, versus frame, it's directly proportional, as you can see on the graph, almost, if not. And then duration versus file size, it's almost also directly proportional. So we'll go to the next. And then the results from the training, this is what we got. The training and validation loss, the loss was reducing as time goes on with the number of epochs. So as you can see on the graph, the training loss is the blue one, and then validation loss is the orange one. So they were all reducing with time or with more epochs or more data that the model was learning on. And then accuracy progression, also the same thing, and the validation accuracy, and then training accuracy. It was increasing with a number of epochs, with more epochs or more data, so it was increasing. Then model convergence. The model convergence, it started training and then to reach a certain point to get some tilt in the direction and stuff like that. Accuracy improvement rates, as you can see on the graph, with more epochs, that's how its accuracy also was increasing, decreasing to a certain point, stuff like that. So, looking at the inference speed and the post extraction, it took 28 milliseconds to extract frames from the videos per video, and then the graph building took 12 milliseconds to build the extracted nodes from the videos, and then the graph attention training, it took 85 milliseconds. So the total is 150, which is below our target of 300 milliseconds. And then with the explainable, so with this one, like let's say we're trying to look for if someone has fever. So if fever equals to yes, so right hand is pinky, and then left hand is index, and then chest center. So the model learns hand to chest motion for this situation. And then the model selection and deployment. And so we selected post extraction, which uses media pipe for extracting those frames, and then graph attention network. So with post selection media pipe, it accepts up to like 583,000 parameters, and then with the graph it handles robust data, and then ONX for Android. That's why we chose this model. And then the deployment pipeline. So the MP4 it's extracted by media pipe on the Android. After extraction, they get a file extension of .npz, and then from .npz it takes to PyG, which turns to ONX for export, and then Android APK of 110 MBs, which helps to translate to a JSON output offline. So this one you don't need the internet for this. We are going to make the system in such a way that you can use it offline to support other areas too. And then with the demonstration, so let me take it quickly through the system, how it works locally on our machine, and then may fall in love with it. So this system, we have implemented the video processing in two ways, using the live camera, and then assuming in a situation where a patient is unavailable, but then they have recorded their videos explaining their symptoms and stuff like that. So the doctor can upload the video and then get what the patient is going through and stuff like that. Yeah, so we can upload a video. Right now I can't do a live camera stuff because I'm using it for recording this video. Yeah. So once you upload the video, the patient, and then you process. But when you're processing, you have to come to this site of clinical results to see the output and so on. Cough, no. 100% sure. Diarrhea, no, and stuff like that. This is the part for the video processing. When it's processing the video, it shows everything here. And then this is for avatar synthesis. This is used when to talk back to the patient. So they can use this. They can type here, do you have fever? So once we can generate how the synthesis understand. You fever have, cough, blood, and stuff like that. That's the gloss, and then you tap that, and then the avatar will translate it back to the deaf patient. Right now we haven't implemented it yet, but we're going to be implementing anytime soon, so that once you guys contact, we can give you the fully working system. Yeah, so that's how the system works. And then the red flag detection. Remember, we uploaded the video and everything was no, so the triac assessment is low, and then so it means we can't tap on emergency. Once it's high, we can tap on emergency or call clinician, those who are in charge of taking care of such a condition. So we can call and stuff, and then we can generate report from what from the video we uploaded and stuff. We can generate that report. Yeah. This system works in different languages: English, Runyankole, and Uganda. So those are the languages, and then the system analytics for generally the things that are working in the system and stuff like that. So on the side here, you can see the form for the patient. This one is supposed to be filled automatically based on the clinical results. Fever, yes, cough, blah blah. So it's not yet implemented. Once we implement this, anytime this results pops up, it's also going to work on this, and then the possible results, palliative diseases, these are the ones. So it's going to bring out the one that is actually the patient is suffering from. So that's it. So we look at the limitation and mitigation. With the limitation, we found when we are extracting the pauses, we extracted only 31.8% of the videos available, and we had 4,026 videos. So we only extracted 31.8%. And then the validation accuracy on average was 57.5%. 0.5% after training the graph attention model. With this, we are not using real Uganda Sign Language dataset. We are using Ghana dataset currently. And then no FST constraints for medical questions and answers flow. And then in conclusion, we have built the first real-time Uganda Sign Language translator, which is working below 250 milliseconds on Android, and then 43.30% accuracy on proxy data. It's a proof of concept for inclusive healthcare AI. And then future works, we want to collect 1,000+ Uganda Sign Language videos, fine-tune the current model we have, the graph attention model we have on real Uganda Sign Language, add FST constraints, and then clinical trial at Mulago for approval and testing and stuff. And then later on, we're going to expand the Ugandan and Yankole prompts to also start working, because currently it's only English. And then references. Yeah, so thank you. If you have any questions, let me know in a comment, and I will get back to you. And then we want to acknowledge Dr. Marvin for taking us through this project. Thank you.